So I'm going to be here today talking about hunting for bugs with static code analysis. So let's have a look at the problem. Why we're actually here, what do we care about? Software developers are human, they make mistakes, they screw up, and there's been quite a lot of that lately over the last few years. We got Heartbleed, Shell Shock, the Ghost glibc bug was pretty bad too, just to pick a few out of the air. And now that they've got nice fancy logos, it makes it nice and easy to make a presentation about them. But mistakes means bugs, bugs mean vulnerabilities. Overall, we want fewer bugs. That's what we're here for. So who am I? I'm Nick Jones. I work for MWR Info Security as a security consultant. Most of my time is spent on web application security or infrastructure assessments. But in a previous life, I was a commercial software developer working with embedded systems. So I've got a bit of an understanding of both sides of the coin there. And I've done some work developing bespoke static analyzers for clients during that time as well. So, roughly what we're going to be going over today, the problems of application security, why we're actually here talking about it, regular expressions, parsers, control flow graphs, and then just a quick look into why you might be interested in these tools and how you can best use them, both as a bug hunter security consultant and what have you, and also from the point of view of software developers. So, to start off, what's the problem here we're really looking at? Throughout the talk, I'm going to refer to a company as a case study, MWR Events, who've been developing a new online events management platform. And they've got a website, they've got mobile apps, they've got a back-end that someone built in some horrible embedded platform. All in all, it's a real mix of stuff. And the developers are average quality, not completely terrible, but equally, they're not particularly hot either. They've got no in-house security expertise, and so they're contracting out to try and find people to help them. So if they want to find and fix all their bugs, where do we start? There's a few different methodologies and mindsets you can apply to this. Broadly speaking, they break down into two categories. You have static analysis and dynamic analysis. So static analysis is looking at an application without actually executing it. You're reviewing the code or the binary or otherwise digging into what the application is built of without actually executing it on the platform it's designed to run on. So this typically breaks down into sort of code review, reverse engineering, analysis of the binaries you get handed, so on and so forth. Dynamic analysis, on the other hand, is your more traditional penetration testing. You execute the application, you interact with it as it's executing, you try and find bugs that way. So fuzzing, typical functional testing, tampering, that kind of thing, all falls under dynamic analysis. Given the talk title, I'm sure it won't surprise people to find out we're going to be focusing on static analysis, and for the most part, we're going to be talking about code review, how to use static analysis techniques to analyze source code. So, how do we do code review? You can either do it manually, or you can build yourself a tool to do it. In the manual sense, you give it to some smart security people who understand how to look for bugs in source code, and they read through it, try and find some bugs. Often you'll find quite a few that way. The other approach is to build yourself a tool, pass your code into the tool, and let the tool understand and reason with the code in order to spot issues that it can understand. So from a manual perspective, I'm sure a few of you have seen things like this crop up in code before. Someone shout out, what sort of bug are we looking at here? Yeah, buffer overflow, fantastic. So that's a nice easy one. You've got a couple of lines of code there, it's immediately obvious when you read it. Likewise, if anyone's done any Android security, they'll tell you that setting JavaScript enabled on your web views generally doesn't end terribly well. So again, single line, nice and easy to spot. Your problem then becomes, it's really expensive doing this on large code bases. I've pulled some numbers off the internet for a few major projects. Latest estimates for Windows and Mac coming at about 45 million lines of code, 86 million lines of code respectively. The new F-35, they reckon, is about 24 million lines of code overall. And paying a security consultancy to sit down and read through 86 million lines of code to try and find bugs in it is a really expensive way of doing it. And to give you an idea of how many bugs that might be, Steve McConnell, who wrote Code Complete, says estimates 10 to 20 defects per 1,000 lines of code. Seems a little high to me, but we'll go with that anyway, which means Windows we're looking at about 700,000 bugs, about 1.3 million for Mac OS X, and our brand spanking new fighter is going to have somewhere between 300,000 and 400,000. And that's a lot of bugs. So how do we cut that down without spending silly amounts of money on security consultants to do this? We use static code analysis tools. So essentially, you build tooling to automatically search your code to try and find security issues that you can write rules essentially for. So you've typically got a very high upfront cost. You're either buying in a commercial tool, the commercial tools get really expensive depending on the scale you're using them at, or you're developing something yourself, and these tools are not trivial to develop, which I guess is why the commercial ones cost so much. And so as a result, there's a fairly serious upfront cost to it. But once you've built it, it's essentially free. You've got to run it, but the actual the cost to run it is pretty much negligible. And you can catch a lot of the low-hanging fruit automatically, as we'll see later on. So, bit of a warning here. In order to get our heads around how a lot of these tools work, there's going to have to be a bit of computer science theory. Apologies to those of you who've done compiler courses already. Equally, apologies to those of you where I'm trying to fit, I don't know, 2 semesters worth of compiler theory into about 15 minutes. This is going to move quite fast. Broadly speaking, we're going to have to cover language types, automata, and then how you build parsers from automata. So what is a language? It's a set of strings of symbols of some description that are constrained by a set of rules. Rules are usually defined by a grammar. So this can be said for human languages, just the same as it can be said for programming languages. And a bloke called Noam Chomsky, who some of you will probably have heard of, came up with a hierarchy of the different kind of constraints that apply to different types of languages. So we're mainly going to be focusing on the bottom 2, regular and context-free. That's where most programming languages fall into. So we're going to start off with regular languages first, taking a look at regular expressions in that context as well. So, like I say, regular languages, which can be parsed by regular expressions. I'm sure most of you have come across regular expressions already. Here we're talking about them in the classic sense rather than the modern regular expression parsers that you'll have used, no doubt, in a number of languages, Python, Perl, what have you. The modern ones are generally a lot more powerful than the classic model and can do things like backtracking. But generally speaking, the same kind of limitations that I'm going to be talking about here are a problem for them. So broadly speaking, regular expressions act as a finite automata, which is a finite state machine. In simple terms, if any of you have used those, you have a list of states and a list of transitions that can be made between your states, and you process your input until you either reach the end or you error out. So very basic regular expression parser, looking for the word nice. So you have your starting character. Is it an N? If so, move on to state 2. If not, you move out to your error state, which here is 6. And so on and so forth, looping through until you either reach success or error. Obviously, if you start using wildcards and so on and so forth, your state machines get a bit more complicated, but broadly speaking, it boils down to the same thing. So how do regular expressions help us? You can match code snippets that look like problems you're already aware of. And there's a few advantages to that, especially in the context of regular expressions. They're very quick and easy to write, comparatively low cost. If you're a security consultant who wants to get a feel for how ropey a code base is, or you're looking for the really, really obvious bugs in some code, this is probably where you start. And basically boils down to, does my code match this very specific known issue that I understand and I've been able to write a rule for? So maybe someone's using some bad libraries, so you can scan through and find any import statements for bad libraries. Calls to known dangerous functions. If you're looking through the code and there's calls to strcpy everywhere, that's probably bad. And likewise, known security misconfigurations. So as we talked about earlier, enabling JavaScript on web views and Androids is bad. So we write ourselves a regular expression that looks for set JavaScript enabled calls. And lo and behold, when you run your regex over your code base, you find this line, so you know that's bad, you can go fix it. There's another example here. We've got some debug statements. They're wrapped in a guard. You've set a constant somewhere that states whether the application is in debug mode or not. And what you care about here is whether you're logging in a production environment. Now, your regex looking for printf statements, which is what we're assuming is being used to log here, is going to quite happily find all 3 of those printfs. So you've got a couple of problems here, though. Regular expressions can't count. You have no way to maintain state. Classically, they can't backtrace. If you're using a modern regex expression, they can to some degree or another. But the issue here, then, is if we go back to the previous code, you've actually got 3 issues turning up for what is essentially still 1. And it's actually not 1 because you've got, it's a false positive because you've got your debug guard in place. In order to check to see whether the developers remembered to put the guard in place, you've got a couple of different options. You can check backwards, line by line, through your code file until you reach either the beginning of the line or the appropriate statement, which is inefficient and prone to false negatives because sometimes you'll catch guards that might not actually necessarily apply to what you're looking at. Or you check the X many previous lines. You pick an arbitrary number, 5 lines, 10 lines, what have you. But that will tend to lead you into a good number of false positives because you're only checking so far. And as I said, you're generating 3 alerts for the same missing guard. So the fundamental problem here is regular expressions are not designed for parsing programming languages. Regular expressions mostly only match regular languages. Most programming languages are context-free. So the next one up the hierarchy, in Chomsky's language hierarchy. And so instead of regular expressions, we use parsers. So context-free languages are a superset of regular languages, as I said, and they're defined as anything that can be accepted by a push-down automata, which is a little bit like a finite automata as we discussed previously, only this time around you have a stack, which means that you can decide your transitions within your state machine both based on the input and also whatever it is that you last popped onto the stack, and you can push and pop to the stack as you need. Kind of a brief idea of how these work. You're reading in some characters off an input tape, you have a stack. Both of those inputs together decide where you're moving next within your finite state machine. So, how does this then apply to a parser? Parsers are generally implementations of push-down automata in some form or another. And you convert text in the form of human-readable source code into some kind of hierarchical data structure, usually either a parse tree or an abstract syntax tree. The basic difference there is a parse tree contains every single token, so you'll include brackets and so on and so forth, whereas an abstract syntax tree purely holds on to the information that is important to actually build the program. Several different types of parsers. I'm not really going to go into the detail there. It's not terribly relevant for this. The one thing to say, though, is that most parsers operate in 2 separate stages, so you have something that chops your input up into the tokens, or strings with an understood meaning, so your keywords in your language or your braces or your variables or what have you. And then once you've finished lexing your input, you then run a parser over it in order to construct your tree of some description. You can combine both. It's not usually done for programming languages. So as an example, we're going to run Alexa over the debug guard example I used previously, and you can see there the Alexa's picked up different types of keywords, function calls, variables, and so on and so forth. And so then once you've lexed it successfully, you can pass it into your parser. And the parser here starts reading from the top, discovers it's got an if statement, so you create an if block. Next up, you find yourself an open curly brace, which means you now know that you're starting a new code block. So from there, all of your printf statements are then attached to that code block, which is then closed off once you then find that final bracket. Now the real power here is that you understand the position of your printf statements within the code, so you can check back up the tree rather than reading line by line without really understanding the context. This is a lot faster because if you're searching back up the tree of source code, that's an awful lot faster than reading back through a 1,000-line text file. But B, it provides the opportunity for far fewer false positives because you have a much greater understanding of context. So, now that we've built an abstract syntax tree, what do we do from there? You've got a few options, really. At a basic level, you can search it for dodgy function calls, debug guards, as we mentioned previously. That kind of thing is quite easy to do, checking for questionable imports. Works the same as in regular expressions, but there are a few other advantages here. A, you've got fewer false positives, as I mentioned. The other thing is it stops you accidentally parsing comments, that kind of thing. It generally makes things a bit nicer. But where this becomes really powerful, that's fairly basic functionality, is then when you start looking at control flow graphs and taint analysis. So let's take a look at control flow graphs. What is a control flow graph? It's a representation using graph notation of the paths that might be traversed through the program at any point. So you build essentially a representation of the possible execution paths that can be taken. Each basic block is used as a node, and we're defining a basic block here as something with a jump target at the start and a jump at the end. So in the context of an if statement, for example, if you look at A over on the left there, we have an if-else branch at the top, which then takes two different paths depending on the variable you input, and then ends up at the same point at the end of it, as you would expect an if-else statement to. In the context of B here, what we've actually got is a while loop or similar. You've got some kind of loop variable that has it iterate between the top and second node repeatedly, and then when you reach your end condition, you then jump out to the third node highlighted. In the case of C, similar, only this time around what we've got actually is a break clause in your while loop or what have you that allows you to jump out to your end condition at a different point to the initially specified end condition when you started the loop. And finally, D is where someone's decided to get fancy and there's two entry points into the loop because someone's thrown a goto in somewhere up in the top block. So that, unfortunately, is something we see on a fairly regular basis. There's still plenty of gotos kicking about. But why should I care about these? What can we do with this? The big, really powerful thing here is it allows you to trace the execution without running the application. So you can use this in the context of disassembled malware binaries. If you're not happy running malware, funnily enough, then that's quite a powerful tool there. But also in the context of trying to find SQL injection, cross-site scripting, buffer overflows, these kind of vulnerabilities, you can use it to trace the endpoint of data back to where it originally came from, which we'll see in a second. So the powerful thing here really is that if the data was sanitized several function calls ago back in another source file, you can trace your way back up the control flow graph in order to find whether the data was sanitized or not between the user inputting it and it actually being used in the application. And that's really quite powerful. So as an example here, I've just thrown some PHP up on the board. We've got a login function of some sort that decides whether a user's logged in or not. That then calls a query function. The query takes some input and returns the result of the query. So your analyzer parses the code, scans right the way through, discovers there's this MySQL query statement kicking around down the bottom. At first glance, that looks pretty bad. You've got variables just being plonked straight into an SQL query without any kind of filtering. But because the analyzer hasn't got the context at this point, it doesn't immediately flag it. So what it does, it says, okay, so what function am I in? This function login query has been called, and we can see that as part of that function call, the two variables that we're passing now into the query statement have been passed in there. So what you then do is look for where that function was called. We know that was up here. So from there, you can see, okay, so again, this username and password's been passed in. Where's that come from? That's come from the original function call here. Again, username and password being passed in, and that came from here. And at this point, the analyzer understands that $_post variables are coming in from the user. There's no filtering going on. That's just straight in from the web server. And so at that point, your analyzer can flag there's been no sanitization. This is probably an SQL injection vector. So you should go do something about it. We'll flag this now. So if you just run a regex over it and looked for query strings where you were just passing those in this context you'd have found it, and that's great. But equally, I've seen plenty of code where people sanitize user input as soon as they get it and then pass it in down at a later point, at which point your regular expression scanning is just going to find, oh, look at all these SQL statements. You find 150 in a web application and 149 of them are actually protected. But who wants to sit down and read through 149 false positives, right? So they have some downsides. As I said before, higher upfront cost to develop. They are significantly more computationally intensive. The research that led to me doing this presentation came from a client project that we did where we moved from some fairly simple grep bash scripts over to a static analyzer, and it went from about a 30-second runtime on this code base up to about 20 minutes. Mainly because I wrote it in Python, obviously not the most efficient of languages, but it gives you an idea of the kind of computational overhead that these bring to the table. So, the thing to note though is despite these being awesome, you can do some amazing things with them, they do all still fit into the bigger picture. You can't just run static analysis tools and expect them to solve all of your problems, either as a developer or as a security consultant. They need to fit in with the traditional manual code review, fuzzing, functional testing, and all of the other kinds of assessment techniques that are already used. It's just another tool in your arsenal. But having said that, how are these tools most beneficial to you, depending on your use case? So let's start with bug hunters. I'm going to define bug hunters here as security consultants, people doing bug bounties where they've got access to the source code, people looking for 0 days to sell to the Chinese, whatever it is that they want to be doing, but not people working on building the software in the first place, and then developers being people who build software who care about their security. So, as a bug hunter, why do you care? There's a few quite useful use cases for these tools. The three I'm going to highlight here are target identification, finding a project to go after in the first place, finding a few low-hanging fruit once you get there, but also, let's say there aren't any low-hanging fruit, it's probably going to give you an idea of where the ropey parts within a code base are. So to start with, we're going to download source for a bunch of projects that have got bounties out, and we're going to pick an analyzer and run the analyzer across all of them. So in this case, I picked Flaw Finder, which is a parser that does some basically really dumb regex style scanning. Essentially it only uses the parser in order to make sure that it's not reading comments or other junk, it's purely reading the actual source code. I ran this across 4 different SSL libraries. Embed TLS is Polar SSL's new name in case anyone wasn't aware of that. But you can see from that quite quickly that OpenSSL would make by far the most sense to go after, given that it's got half as many alerts again as any of the other libraries. There's a reason that people are finding Heartbleed and things in it, and it's been spun off as LibreSSL. So the kind of stuff that Flaw Finder gives you back is a report that looks like this. So we found PKCS11.c, online 871 is using string copy, and that in and of itself, maybe that's not that important because they've already checked sizes of what they're string copying, but generally speaking, not good. You should probably be using one of the safer functions. So you'll find if you run Flaw Finder across one of these, a big long list of all of these kinds of things. And so that gives you an idea of where you might want to start looking. It's also really good for picking up a lot of the lower hanging fruits and actually some slightly more complex bugs too. We talked already about using taint analysis essentially to look for your data sinks and then tracing back up your control flow graph in order to understand where that data's come from. That's quite powerful for spotting a lot of the classic user input type attack vectors. But moving on from that, actually, you've also got use after free detection to some degree as a result of having this control flow graph. But you can track pointer allocation and deallocation as you go through the application. You can look at all the different execution paths because you know that because you've built your control flow graph. And you can use that by keeping track in order to detect whether someone is referencing a pointer after it's already been deallocated. Likewise, you can use that to check for things like double freeing of memory and so on and so forth. Because you have that context and you have this understanding of how the data has flowed through the application. So to give you some examples of some tools that you might find useful for doing some of this stuff. Flaw Finder, as I illustrated previously, good for C, C++. Graudit stands for grep rough audit and has a bunch of signatures for a few different programming languages. That tends to generate a lot of noise and a lot of false positives, but if you're looking for target identification or trying to work out which areas of the code base are particularly ropey, that's quite a nice place to start. If you're using Java, you might have come across Find Bugs previously. Find Security Bugs does, I think it's 80 different classes of bugs for Java web applications mainly. And that will catch a lot of the low-hanging fruit or minor issues like incorrect cookie flags being set, you're not setting HSTS headers, that kind of thing, along with the sort of the SQL injection and other user input related bugs that I mentioned previously. Rats is quite hard to find a copy of these days, it turns out, but most of that's now been built into a commercial tool called Fortify, but that covers a number of different bug classes for a few different languages. RIPS works really quite nicely on PHP. There's 2 versions of it now. It used to be open source, there's now an open source and the commercial. The commercial does a lot more of the in-depth control flow graph analysis and so on than the open source one, but the open source one will still catch quite a lot. And if you're using Ruby and Rails, then Brakeman's also quite nice. If you're going to do what I did, he says, with his clicker not working, and build your own, then there's a few options for that as well. So the analyzer built into Clang is really quite powerful as is, and will do a lot of C++ static analysis for you simply when you build your source code with it. But also because of the way Clang works and the way it's been nicely separated out into different chunks of libraries, you can actually use Clang's front-end syntax parser and so on to build an analyzer off the back of the abstract syntax tree it builds. There's quite a steep learning curve there, but Clang is really, really powerful. So if you're looking at anything Clang supports and you wanted to build your own, that would be one of the places I'd recommend starting. If you want something quick and dirty and you're familiar with Python, then there's a library called Ply and a variety of different libraries that build on top of that. PlyJ for Java, for example, which was what I ended up using, which will allow you to create abstract syntax trees out of inputted source code. It's pretty slow. Like I say, Python's not the fastest of languages in any case, and Ply's not been terribly well optimized, but as a quick and dirty starting point while you're trying to get your head around how a lot of this stuff works, that's not a bad place to go. PyParsing likewise operates in a similar fashion to Ply. Then you get onto some of the more academically inclined or grammar-focused tools such as Antler and Cocoa. So they require you to define a grammar for your language. Helpfully for a lot of the major languages, people have already defined grammars and posted it on the internet, but you can then use that to generate code for Java or Python or C. I think there's a couple of others they support, which allow you to auto-generate most of the cruft for parsing your language, and you can then add in your own functions for, oh, okay, I've come across a variable, what do I do with it? I've come across an if statement, what do I do with that? Which you can then build on in order to build your own analyzer. So now, if I'm a software developer, what might I be interested in here? The big one really is how early on you can catch bugs with static analysis versus waiting for the traditional pen testing cycle to come around towards the end of the application's release. The earlier on you catch a bug in the development lifecycle, the cheaper it tends to get, and you can build these tools in as part of your existing tool chain or other tool sets you're using in order to make it as easy as possible for your developer to use it. And if you've got a large development team, you can have 1 or 2 experienced developers or people who understand the security implications of some of these bugs, build your tooling for it, and then hand it off to everyone so that you've got the same level of static analysis checking being done both by your 20-year veterans and the interns you've hired in for the summer. So one of the places this is really powerful is in the context of continuous integration. So some of you will no doubt have seen the buzzword being thrown around. Essentially, the idea is every time someone checks code into the central repository, you compile it or interpret it, run the tests across the test suite across it, and then there's a report as to whether your build failed or succeeded, and then whether the test suite did likewise. Which means that every time someone pushes new code to the repository, it gets checked for bugs in a fashion that everyone can keep track of. So you've probably seen some of the tooling that's been used for this kicking about. Jenkins and Hudson are 2 of the major ones. You've got some commercial offerings from Microsoft and Atlassian, and Travis is also fairly big. Incidentally, if you're ever on a network pen test and you find one of these running, they're usually a goldmine for remote command and code execution. Jenkins, for instance, by default has no default credentials, and you can upload your own build scripts and just hand it a bash script for it to go run on the server. So that's quite good fun. But broadly speaking, the workflow that most CIs follow is developer checks in code to the central repository, server compiles, interprets, etc. Test suites are automatically run as part of that, and so we bolt our static analyzer in there. And so most of the tooling, this is Jenkins, but most of them will provide you a nice little graph that shows whether you're passing or failing and how much you're passing and failing and so on. But catching issues as they're introduced to the code base is so much better than catching them right at the end. It costs you so much less. You have the developer who developed it there and then. He sees it as his mind is in the set of that code. He understands it instead of having to come back 6 months later and go, what was this Perl I wrote? I can't read it. And catching regressions in code before they hit production as people introduce bug fixes is really quite powerful too. I've got a case study, we'll talk about that in a second. But also the fact that it runs automatically with no developer input required beyond their usual checking coding means that people can't escape the tests. There's no, oh, I forgot to run the static analyzer that time round, and oh, look, these bugs slipped through the net. It all happens automatically. So as an example of where it would have been really useful for someone, Marks & Spencer's had a fairly major data breach back in October of 2015, where as part of a bug fix or feature enhancement or whatever, a developer managed to make it so that when you logged into M&S, you were presented with someone else's user details, including partial credit card numbers. So it took them about 2 or 3 hours to find and fix that. Meanwhile, it was up on the live site. Whereas if you'd had a decent set of test suites as part of your continuous integration, you could have caught that by using appropriate test data. Static analysis wouldn't have been particularly useful in that particular bug example, but it shows where that kind of automated testing from a security perspective makes an awful lot of sense. If you're a developer and you're short on time, like a lot of developers are, you might be better off buying in a commercial static analysis tool. So there's a few examples up here I've pulled up. Veracode, Coverity, Fortify, Checkmarks, Clockwork. You've probably seen a few of these names kicking about at security conferences and things, especially if any of you were unfortunate enough to take a trip to InfoSec. These tend to be very powerful once they're built right. They require an awful lot of tuning of the rule sets, writing your own custom rules and so on and so forth, in order to tune down the amount of false positives they generate. It's well worth taking the time to do that if you've got a large code base and a large number of developers, but that plus the initial licensing cost can make for quite a steep budget. I've just pulled a screenshot of Coverity off the internet to give you an idea of roughly how they look and how they work. So this has been run across a large code base. You can see there's a big long list of issues up the top, and while I'm sure you can't read that, it says that it's found a buffer overflow. Because someone's not been checking sizes of data being passed in correctly. So a few places where us as security consultants, I'm sure I'm not the only security consultant in this audience, might be able to help some of their clients in several ways, but the obvious 4 that came to mind while I was writing this, identifying where the security risks are likely to lie in any given code base. Whatever your application, you've got situations where the code is likely to be more security critical than others. Let's say you're writing an Android app, the masses of UI guff that Android requires you to generate is probably not going to cause much of a security risk, whereas your root detection, say, if you've got a fancy app going on, might be a little more important. So understanding where the key points of your code are helps you to tune the rule set to focus down on the really important parts. Some security consultancies will offer services for writing custom rules for existing static analysis engines. What I talked about previously with commercial tooling requiring a lot of tuning and additional rule writing in order to get the most out of it, hiring someone else in to do that for you might make sense. In the extreme cases where you've got particularly unusual either environments and libraries or programming languages being used, it might make sense to be developing bespoke tools as we did. But that's a pretty expensive option for most use cases. And finally, advising on how you can integrate all of this tooling best into a development lifecycle, depending on the client's own environment and needs, is also a place I think security consultancies can add a lot of value. So, conclusions, what have we covered? So static analysis overall can provide a lot of low-cost security checking for comparatively little effort for developers, and as a security consultant will allow you to find some classes of bugs quite quickly as soon as you sit down at your engagement, or if you're bounty hunting, might help you both work out what targets to go after and also where to look once you get there. If you are going to go down the static analysis route, especially if you're looking at building your own tooling, while regular expressions and a few quick bash scripts running grep over things will catch some stuff, really being able to build abstract syntax trees and then control flow graphs off that gives you so much power to do all kinds of analysis of the application that it really is worth looking into doing that if you can. And at the end of the day, all of these automated analysis techniques do complement traditional manual assessments. You're not going to be replacing pen testers with this anytime soon, unfortunately. So, thank you for listening. If anyone's got any questions, there is a man at the back with a mic, so if you could stick your hands up, he'll come round to you with a microphone and we can get started.